This analysis was based on a very large merged 3D that was offered to Tom by a buddy friend of his, mostly for research purposes, but it covers 2 counties in south central Texas, and the original volume was almost 900 square miles. But we sectored out a piece of it. That was elapsed area, not all live traces, but we sectored out an area of that for me to work. And the results presented here are really collateral to this envisioned research project. It was, so be advised, it was not an exploration or exploitation project per se, but so much came out of just using the software and in a thoughtful manner. And I will explain some guidelines, and then seeing what we could see. Although the Eagleford was the focus of all the work. I also changed the title up a little bit because this work resulted in a sub-seismic resolution of stratigraphy and facies for the Eagleford group that even startled my colleagues who had been working with the software for 3 or 4 years by the time I came on board about a year ago in November of 2014, I guess. 2014? Yeah, 2014. So anyway, want to remind you that the principles herein are completely transferable to conventional plays, and that because they're quite fundamental. What we've done are quite fundamental. So, getting on with it, I'm going to do a brief overview, and then the talk will be in 4 parts. If we start to run terribly long, we can cut it short. If you're not satisfied with how many well calibrations you see in it, we can look at that stuff on a sidebar afterwards if you want. But I did try to up the ante there on that particular part. So in terms of the overview, we're going to talk about the project basis real quickly, the tools that are in use with Paradise. I'm going to give you guidelines to multi-attribute analysis because a lot of people haven't a clue how to apply multi-attributes successfully. Helps to have a really good piece of software to work with. I'm going to show you how the attributes were selected for the self-organizing maps that are going to be the result sets, we call them. I'm going to use some jargon here, and I want you to let me know if I lose you at any point, because there are some key points I'll try to do my best to be clear about. And then I'm going to show you the conclusions before we even get started so that you'll know where we're headed. Oh, sorry, excuse me. And again, principles are applicable. Okay, I have a pointer too that I'll use from time to time. So I used eventually about 216 square miles of that merged 3D I referred to. It's pre-stack time migration. They gave me 0 to 5 seconds, and importantly, the data was sampled at 2 millisecond sample interval. I'll explain why that's important in a bit. I was given 4 mapped horizons ultimately. I repicked on every line in this huge volume on the Eagleford Shale and the Buddha because they were going to be part of my delimiting of the data set that was focused on in the end. I have used the Upper Eagleford pick itself only for illustration purposes, and the Austin Chalk came in later, so it was never picked on every line. And you'll see the difference that makes in some of our illustrations. They're less pleasing in a way, but they still work. I had over 300 wells to work with, type logs that were less than satisfying only in that they didn't include enough of key type logs to satisfy the kind of work I like to do. But I was given horizontal borehole montages. There are only 9 calibration wells, but that was kind of sufficient to capture most of the zonation variation that I discovered. These were pilot holes, vertical pilot holes, and with all the bells and whistles. And then, importantly, part of the research project was, which we have completed the first phase of, we're not going public with it entirely, but I'll show you some of the high-level results, is that we were given 274 of the horizontal wells with a spreadsheet of numerous non-seismic attributes. These were geologic and petrophysical measures from these wells, and it was phenomenal how well they worked with the observations I'd already made. So, alrighty. So the tools that we use in Paradise are basically three. We do, originally we do principal component analysis, and this is where the key attributes that you want to combine in your self-organizing map can be selected. And this is sort of the rule of thumb that comes from experience, my own and others, that you generally tend to select 2 to 5 of the prominent attributes. Here's where 5 are selected, from 1 to 4, or maybe even 5 sometimes, of the prominent eigenvectors. This is an eigenvector. You'll punch on that, you'll see what comes up, and I generally pick the ones that are at least in double digits. And then I'll pick however many I'm going to pick. This is an older example, so it's actually from a tight carbonate project where I picked fewer. But in this case, and in every case, I always check. We have a little cumulative button here. Check to say that the attributes that I've selected, the number of them represent or comprise over 60% of the data. In other words, they apply to at least 60% of the data, because you don't want too few statistics. You need the right number, not too many and not too few statistics in order to get a good answer. Then we go and take the selected attributes that we have, and I'm going to show you the list that I used in this work, and we make a self-organizing map. These are called Cahonin maps, if you're more familiar with that terminology. This is a learning machine, and it learns what the data has in it, and it classifies the data in clusters, and it classifies them in the number of clusters that you suggest. It's called a topology. So mine are going to be largely 8 by 8, a topology of 8 by 8, which produces 64 neurons, or it's going to go out and classify the data into 64 little partitions. That can be too many, although 8 by 8 is a real good place to start. But for some project, for some problems or some geology, that could be too many. You get it cut up in too many fine pieces and you can't observe the right thing, or it can be too few. So it's the lumper splitter kind of notion. But I went to 5 by 5 and found out that I didn't get a very big change in what I saw. So I was very satisfied with my result. But this shows the geologic features anomalies, and it does enable us to do very specific calibrations. Yes, sir, Tom?
So you started with 5 by 5 and that was not...
No, I started with 8 by 8. I went to check what would happen with 5 by 5, and I still got remarkable resolution. So there's no point in doing that.
Is that an immediate run? You run it immediately?
I run it, yes. You make these selections, you code it up, and depending on how large your data set is and how many attributes you've got in there, it may take, this project was 10 square miles and they took minutes. I think the longest thing I ever ran took 13 minutes. This one was much bigger, and so hour and a half. You know, sometimes I would purposefully run things overnight so I didn't have to wait for them, that kind of thing. We also have interactive 2D color maps. So our neurons will be laid out given a color map. And I used mainly just a couple of different color maps here, and I'll try to help you keep abreast of when and why I changed the color bar. So, all right, let's boogie. All right, guidelines for multi-attribute analysis. We're collecting these as we go, and we're learning. We have a nomenclature. Your seismic data that you're given or you have would be your base survey. And it's a lot of attribute generators require 32-bit seismic data. And we have found that you get a much better resolution if you're at least sampled to 2 milliseconds. If you have more 4 millisecond data, you can resample it in your interpretive software down to 2 mils. We have some wild men who want to go down to half a mil, so, once they get power and they go crazy. So anyway, we run all the attributes from the same base survey, okay? You don't want to mix apples and oranges. We do not combine attributes from different classes. So we do the instantaneous attributes or geometric. We rarely use wavelet, but wavelet are very dominating And so they will, if you combine them with anything else, they'll wipe everything, you'll never see your other stuff because they'll be dominating. Anyway, the reason is that these attribute types have different data distributions that can be incompatible, so they won't give you a good answer. We suggest you use a suitably focused geologic interval that contains whole genetic units, and that's me talking, genetic units, with horizon delimiters so that you return coherent statistics. You don't want to cut across, a Facies band or a geometry that's, you'll only get half of it. You want to get the whole thing so you can see the systematic variation. And we use judiciously the 2D color map to produce greatly enhanced images. The other thing to remember is what I said about picking on every line. Ooh, sorry. That didn't want to stay. Picking on every line, it'll be worth your trouble. I'll try to guarantee that. But okay, so I'm mainly working with the instantaneous attributes, and I first worked with them in 1982. So but I only had 3 then. Now we have 16 or 18. And so the attributes for the PCA is to put the whole class of those attributes in them. And these attributes are particularly useful for stratigraphic and facies determinations. And what the PCA does is dimensionality reduction. And it gave me back 9 attributes in 3 different eigenvectors, 3 each it turned out. And there they are, not in any particular order except alphabetic. But this is my base survey. Real part is highlighted because it's almost another copy of your base survey. But the base survey is included in this list because it's used to prune out null values. You don't want one of your neurons being classified null. It's just a waste of good neuron. Okay, so
different volumes that are generated.
They're different seg-y volumes, absolutely. Okay, these are all separate. These can be generated, outside Paradise. We generate some inside Paradise. We will eventually be generating them all inside Paradise. We're working on that now. Instantaneous phase is good for discontinuities and continuity and discontinuity, both in structure and strat. The normalized amplitude is also known as the cosine of instantaneous phase. It gives you the sense of peak and trough value. With the relative acoustic impedance gives us our geobodies, which you're going to see. And imaginary part and real part together give you envelope, which is the total energy in kind of like amplitude, but it's the total energy. And all these are instantaneous, which means you got a value at every sample, and they are normalized by standard deviation, these attributes, so that so that you get the results that we get. The other 3 are present, but these 5, we have a new utility that allows us to tell for every neuron what attribute really went into Composite, and the things I'm showing you today had some combination of these 5 more than anything else. But I have one geobody that I found late in the game where trace envelope is important. Okay, we're going to get to the pictures here pretty soon, but I wanted to give you my conclusions before we got too far. So we have a terminology, and I'll show you this again. The upper Eagleford Marl can be readily distinguished and separated out. The ash beds at the top of the Eagleford Shale can be distinguished and readily, because they're non-reservoir, can be mapped and separated from the reservoir. There's if you may know Pepper Shale. By this company, it was called basal clay-rich facies, or basal clay shale. And it can be mapped and separated from the underlying Buddha and the overlying Eagleford Shale target. The Eagleford itself had 2 reservoir types, basically. An upper low resistivity and a lower high resistivity. Occasionally when a borehole went lateral from one to the other, it would be called mixed. You will hear me say high res and low res, and I apologize, but I do not mean resolution in this case. I'm going to be meaning low resistivity upper, high resistivity lower in the reservoir sense. Here we're separating them into at least 6 non-layer cake zones. The non-layer cake was a real surprise for a lot of people. And it also includes at least 2 unrecognized and underdeveloped geobodies. At least one of them we know to be a sweet spot. We know that it has the characteristics and was a target, but often they just blew it, they just missed it. Because our attributes return back from attribute space back perfectly into survey space, we never lose where we are in the scheme of things. So the company had trouble seeing faults in the Eagleford. We do not. We're resolving them in several different ways. And then I tried some spectral decomp work, and we found out that it's the selected frequencies that I chose to work with as a base survey had its best results in the Austin Chalk and Buddha, but also recovered interesting things in the Eagleford. Okay, here we go. Stratigraphic results. I borrowed this. One of the things you don't get when you're doing mostly a research project and not really exploration is you don't get a column. And so I borrowed this from an article that's in press. This is Mike Fairbanks at Apache and 2 guys from the BEG, Steve Rappel and Harry Rowe, who long time, big time Eagleford players. And it was suitable because it's very similar enough so that for my study I could lay in the Buddha, the basal clay shale, the high resistivity unit, the low resistivity unit, Eagleford ash, although I'm going to come back to that, the upper Eagleford marl, and the Austin chalk. And I put the well top colors, and this won't make too much difference to you. But I'm showing another feature here. I'm not saying this ash bed fills lows, but I'm showing a red and gold distinction here because we have an up dip red zone that I'm going to talk about that downlaps, and then a gold zone that overlays and onlaps that. And here are the red zones. This I've done just recently, and I don't know how well you can see the distinctions in the color. It doesn't look too as good as on the screen. But suffice it to say, I'm going to show you the distinctions between 2 and 2 of these colors with a little animation. Okay, first of all, the lower deep rusty red zones lap out down dip, and they also reappear over here, but they're not present in the middle, right there. They are the high resistivity lower part of the red zone. The red zone is only one part of our overall stratigraphy. It's the lowest part on top of the basal clay shale. Okay. These next 2 colors, that was 61 and 62. 63 and 64 neurons are painted on, I've got to say this was progradational. Aggradational on the top of this up dip are some 63 and 64. And down here, these are what I had identified and calibrated in wells, the Eagleford ash. But they're the same. If they're the same neuron, captured by the same neurons, they are the same facies. There's a similarity there. There's also a change in the 62 in the number of the type of attributes that bring it out that tell you there's sort of an unconformity between this lower and this upper. But this was just fascinating to me. What I don't know, what this helped me understand is all this. This is bentonitic claystone present. Understand why I had evidence, if you will, that this upper part was kind of commensurate with that, although I don't think it's very much thickness. It's a veneer relatively, and I do not know whether this 63 and 64 are coeval in age, or I believe that my ash, like I said, it fills lows, and it could be this, or it could be this stuff carved into it, except it's so flat, I really think it's part of this low resistivity. It is low resistivity, I believe it's part of that low resistivity zone. So like I said, this is something I only got a chance to play with lately. Okay, when I started, my first steps, when I started, I didn't have my picking all done, so I did a SOM just with time delimiters, 1.5 to 3.2 seconds, because that was the extent of the height of my Eagleford. And I used a default color bar. This is what we call the 8x8 topology. This is a default color bar. And you see, while the Eagleford, where I can tell where the Eagleford is, it's not very distinctive. So I went in and I punched two different color changes, the purple and the yellow, and it reset some nearby colors compared to these reds, and suddenly the Eagleford is standing out like a sore thumb, looking quite unique, as I kind of expected that it would, okay? And that's just from tweaking the colors in our 2D color map. Okay. But how unique is it? Well, was I delighted to see when I turned off all the colors except those that were contained in the Eagleford, and I also included one of the neurons that was an upper Eagleford color just for contrast because it's green. And this is the sequence of colors in that stack. And lo and behold, there's a section cut into the Georgetown that has that same Facies configuration, and there's a piece down here we didn't even know, we couldn't even calibrate to, but I suspect is the Pearsall. So handy dandy figure number 2 borrowed from this group, but this goes back even further to BEG guys. And I added this little guy because the Pearsall has characteristics, apparently, just like the Eagleford, when I use this statistical band, okay, this broader statistical band, because we're going to use a narrower one real shortly, and for the rest of the talk. Those scours are right here into the Georgetown, and you will see some caricaturing that I've done on the Eagleford and the upper Eagleford marl. Our basal clay shale appears to be sort of blanket-like through the area. We have the red zone that covers the entire Eagleford reservoir area up dip, and down dip it laps down. The gold, I call this gold overlay zone, and there's a gold zone out here, and I have a geobody that occurs in there. All high resistivity reservoir in this zone. The low resistivity part of the gold is above that. Then there's an unconformity in the upper Eagleford marl. Didn't do a lot with the marl, but you're going to see plenty of figures including it. Okay, now we're going to talk about facies architecture. I'm going to repeat this slide twice because if I lose you here, boy, I'm in big trouble. This is good stuff, but it takes a little bit to talk about it, okay? The client provided me this piece of section, conventional seismic, conventional color bar, the Austin chalk down to the Buddha, 2.5, 3, depends on how you count your cycles when you've got stuff like this, but not many peak trough cycles. And not much resolution. This section reminded me in the 80s, before I started working with instantaneous phase, people used to boost the seismic to get it to look continuous. This looks real continuous, but there's nothing resolved there. Nothing like you're gonna learn can happen. They told me that the Eagleford objective was about 14 mils thick, so that's 7 samples here, 108 feet. That's possibly at tuning. The tuning could be 100 feet, it could be 150 feet, but anyway, so the entire Eagleford group is only 28 mils. Interestingly, 14 samples, and by and large, it's just kind of crazy, but the Eagleford and the basal clay are roughly 14 different color bands, so that I just don't know what to make. And they talked about influence. One of the things that we don't have to worry about in our normalized standard deviation world is tuning, absorption. We can find it with attributes. We can find absorption with attributes or attenuation, but they are not big issues because of the way this data is handled. And you'll see that. You'll see very discrete results. Okay, so I think that's all I wanted to do. Notice that Sitel gave us permission to use this data. I haven't said that yet. Okay, now we're going to be on the right side. Here's my 8x8, and I used, maybe you're familiar with Map Shade Dark. Is a color bar that came from an interpretation package that we could migrate into Paradise. We can do the opposite. We have color bars in Paradise, and we can move them out into software. Map Shade Dark just happens to work well with an 8x8. And so I've taken it, and you'll see some examples of where I've taken it out and used it in SMT. So, for example. But at any rate, so here, what you need to know, you also need to watch this. Whenever I make this note, it's either going to say seismic thickness is 100 mils or 110 mils, because that's what I chose for this new statistical base for focusing in, and with this focusing, we got all this detail. This surface behind here is the Buddha. It is a horizon in Paradise. There are a couple of color bands beneath this that are the Buddha. This is the basal clay shale, and with this color bar and this SOM, the basal clay shale is gray like this everywhere in all the wells that I calibrated. Okay, it's just a single gray band. Really distinctive, mostly non-reservoir, so it can be pulled out of the picture. And one of the things we're developing is the ability to map on the neuron color interfaces, which is going to be really powerful. This is that red zone lapping out with the black, that, you know, so all the red zone is up dip. I don't know that the example that I am going to show you, let me look, has it's not that I think, I know. Oh, no, it's everything's thin. This is, you know, the whole thing. The whole Eagleford group is only 260 feet. So, yes, sir. Yes, ma'am. What? They're thick. So they have some thickness. Yeah.
Patricia has been kind enough to say that if you don't understand the principles, to let her know, and she will backtrack and explain them. But please keep regular questions to the end of the talk.
And I can pull those out, Walter. I have examples. I can pull them out. I have a hard enough time remembering the neuron numbers sometimes. You know, it's detailed. Okay, so what do I do with this geobody that I found? One of the things we can do is we can focus the classification on a horizon, or we can take that horizon and move it down through a body, and that's what I did here. So I took the top Eagleford and I moved it 12 milliseconds below the top, its normal position, to intersect that geobody. And now, this is where I need to tell you about color bars again, because I found this thing with Map Shade Dark. It was rust colored. I had a devil of a time extracting it with rust for some reason. I think there was, too many other things that also had a rust color or something. So I went to this color bar where it resolved with 3 neurons, as I'll show you, in this red body. So don't be alarmed. This is still the rust geobody, still called the rust geobody by me, but it is red. But what I hadn't expected is this flange or backdrop that is two other colors. And think of it like this. I put this little silly thing in here because I'm cutting across where the flanges are, where this whole fairway, I call it, is wide. And then I'm going down 4 more milliseconds, and this thing is narrow. To give you an idea of the 3-dimensionality, the thickness variation, and also with these wells, that they didn't quite get there. See, that borehole is above this red, and so on. They kind of missed this thing, and they knew it. And so first thing wanted was a flat map so they could see where they should go looking for it, because it is a high resistivity. So this is just the extraction of that geobody separately, and those are the 3 neurons that find it. Mostly the 60 red, and then the oranges and the other oranges are down, mostly down dip. Those variations are real. There's an expander down, slide expander down there. Those are real features. Okay, here's my well calibration. This is from our own software. This is a log track display. This is the feature that you, and oh, by the way, I have been lovingly referring to these as bacon strips. Can you tell why? Okay. I just couldn't help it. I go, bacon strips. Anyway, again, we're at 100 mils, which says the Buddha is below my surface, which is the Buddha pick. You see how smooth that is? It's smooth because I picked it on every line. There's the basal clay shale. There's the rust zone. And this is the deviated borehole. They gave us only 3 ways to locate the deviated boreholes, and this green is the first perf, purple the mid perf, and this rust one is the last perf. So that's how we found these in 3D space from them. This is the top of the Eagleford. That's the ash bed underneath it. The upper Eagleford is largely magenta and this purplish color. And again, the grayish enveloping the rust is high resistivity, and the plain gold and the ash beds, which remember were 2 neurons, 63 and 64, are low resistivity. Here is the Buddha, the pepper shale or basal clay rich shale, very distinctive. This was called the target zone on their the little go-by logs that they gave me, but they missed it entirely. And you won't remember, but if these are dark green, these EUR numbers, that means the volumes come from high resistivity pay. When they're light green, low resistivity pay. This is the low resistivity pay, and this is where they recovered all the volume. So they missed this beauty, which is the thing that's brittle and would frack, and you know, it was their target, but they missed it. And these are normally compacted shales. There's nothing too fancy, but this was my very best example, and so I spent a little time pulling that together. Okay, all right. One more geobody cropped up. So, and this, unfortunately, is not calibrated, but we have a vertical well nearby it, and this geobody I call the yellow-brown geobody. And their cluster of horizontal wells either went above it into the marl or below it into pay that is high resistivity. Now you remember the red that was way outboard. This is that red. It is 61 and 62, not the ash beds, and they're low down there, see? And then there's the brown and yellow. Now, because there's the same yellow in the Austin chalk, I extracted this geobody using only the brown, because they stack everywhere on top. The yellow stacks everywhere on top of this, like you see. This is a Timeslice, just giving you I wanted to see, because these look scooped, like they had scoop bases, I went out to see where are these nestled. And in a Timeslice, you can see the brown yellow. This is up section, down section. The gray stripe is the Buddha top, so now I have that in, but I don't have the whole of the Austin chalk here, because this is just the top of the Eagleford marl mapped top. And but at any rate, there's the Eagleford between those, Eagleford shale between those two, and you can see that it's kind of nestled in there. And it was higher up than the rust zone, and you can see that because the red's coming down and the rust is here. Now, we also have another feature in our software that allows us to put a probability filter on top of anything we're looking at, and it comes out white. This is a 10% probability that I have this set to, but we can do whatever we want. But when you choose a small probability, the sense is that area is anomalous for whatever reason. And in this case, we believe it's the hydrocarbons. The Buddha lights up some places. You can see that on this example right back here on the poster. That's Buddha stacked below Eagleford, all brightened up, done by another worker. And anyway, but what's neat about this overlay is you can see fault traces that you might not have appreciated. And this break also resolves as a fault trace looking thing. So there's some subtleties in almost every view we make through the volumes. Okay, now I'm going to summarize this bit before we go into the next section. And this is from the research. And what, through the magic of Disney, we have a gentleman who helped me pull out my rust geobody and my brown geobody so that you could see how they are situated. Remember, the brown is on top. It was put on top here, and there literally is, it literally kind of seems to wrap around the rust zone down there. But I had already classified the red zone, which later I broke into two parts, because there are 2 segments over here and 3 segments over here, and I just felt that they were, and they appear to be, given the parameters, appear to be slightly different. There's a zone I called gold overlay, and that's where the gold overlays the downlapping red. There's a place, this was sort of named later, gold gap, because there is a time when the red by this time has lapped out, and the gold, it can be narrow, it can be thick, but these wells are all in gold gap, actually. Only one segment came out rust geobody 1. And a segment here is a group of the wells. So these numbers of wells add up to that 274, for which I have the tabular data, petrophysical and geological parameters that were put into a SOM and sectored out these wells in the same way I had done visually on the color. And then some, because there was a group, segment 12, that had a piece in the red zone and it had a piece in the gold overlay zone. And so I separated the wells, and sure enough, their parameters were more consistent with the group that I moved them to. So this is how you can have a 4x4 topology, 16 neural clusters, but you can get 17 segments out of it, because you can observe that you need to break them down. So this is close, but this was done with just 4x4 on this tabular data. So, and that's about all I can tell you about it. But this other number is the number of calibration wells that are in that zone. So I don't have a calibration well for every zone, but when I'm depicting them, you can see the neighboring zones well enough. Okay? So now we're going to talk briefly about resolution of faults. And how are we doing, everybody? Everybody awake? Okay.
Yeah.
This part's short. This particular client had used similarity as a singular attribute to try and look at faults. And they had provided me a really lovely map and so forth, but it was on paper. So I went in and across this well, which has its vertical here and its deviated borehole going down that line, basically, that inline, you can't see an image going across that, and sure enough, they didn't deflect a single picked horizon through there, because they can see the faults coming. I picked this fault from probably instantaneous phase data, and you can see it goes forever. But these all look like they cut off right before you get to the upper Eagleford marl, so at the base of the Austin Chalk. And so their feeling was that the faults cannot be observed in the Eagleford. But you can see the Austin Chalk is deviated there, not so much in some of the other positions. Okay, and that's the vertical pilot well with a gamma ray and a resistivity curve. Okay, this is a geometric SOM result. So a result set from having run geometric attributes. And the PCA here suggested a reduction of the 25 input geometric attributes down to 10 from just the first 2 eigenvectors, 5 from one, 5 from the other. The first 5 were all different varieties of similarity. The second 5 were 5 variations of curvature. So what's important in this seismic data set for this kind of geometric attribute are those types, and no others, unless I went well beyond the 60% and just gathered things. But it wasn't necessary, because this well had 6 faults in it, and they had never seen any faults. This is geometric classification on the Eagleford top that's been pushed down into the high-res Eagleford pay, which, you know, is a little, probably a little more brittle, but we could bring this up and down and we can see faults in detail everywhere. This well had 2 faults in it, and I actually did a better resolution of that using spectral decomp, which we'll see in a little bit. So that's you've seen that map in the thing. So this is the Downdip area, squeezed just a little bit. This is using the color bar that I call the rust zone extraction color bar. Grab me one of my waters real quick, please. And I tweaked one of the colors to be white in the core, thank you, in the core of this, just so you could see it better. And I turned off the enveloping 60 reds. So 58 was turned white, and 60 reds were turned off, although you can't tell it. they were turned off in this view. And so were a bunch of other colors, as you can see. But this is just another way to look at that zone. And then squeezing it a little bit, I could accentuate sort of simple looking normally faults, but there are a number of compressional faults in here. You know, and I probably could have picked faults in here for days. I mean, every time I look at it, I say, you know, why didn't I pick that? Why didn't I pick that? You know, why didn't I pick, you know, this red-white place, you know, or something else? But suffice it to say, we can see faults in the Eagleford with just, this is the instantaneous sound, the original, not geometric, you know, not those things that are supposed to. But when when you're working with instantaneous measures, you're seeing high frequency, you're inherently high frequency, and you're seeing continuity, discontinuity. All righty. This is just a close-up of another really spiffy fault. And here again, bacon strips, and the map shade dark. This is the red, the 63 and no, the 61, 62 downlapping and breaking like scooting away until it finally downlaps, and it downlaps. This is sort of gold gap. This is gold overlay, and then we're down in the rust zone, high resistivity where it's gray, and then just a little bit of low resistivity stuff there, and again the ash beds in that down dip position as we saw them early on. We're right in the middle of the data set. This is near some of the best wells in the area. A million, oh, excuse me, not a million. Gosh. Anyway, most of these are like 250,000 to 300,000 barrels of oil equivalent. This one is 1,000 barrels of oil equivalent, some of the wells that are in this vicinity. Again, we're on the Buddha horizon. We're seeing the basal clay shale, 110 or 100 mils there. So, and I think that's the last one there. Now we're going to talk about spectral decomp, unless nobody wants to hear about spectral decomp. But just this is some of the coolest stuff, you know, and that I don't purport to understand completely. Yeah, but spectral decomp is also a useful tool for seeing sub-seismic, they say. This is the conventional wisdom. I think it's true, but I wonder about anything that's normally based on amplitude, because amplitude is inherently not discrete. You know, amplitude can change with so many different kinds of stacking. You can have silt on silt and it'll make an amplitude in some parts of the Gulf of Mexico. But it does give us an opportunity to unravel the signal into constituent frequencies. And here, with our multiple normalized instantaneous attributes, without, you know, tuning problems and other things, it's really the envelope component that helps quantify thickness variability, and the phase components that help us detect the lateral. This is my shorthand. I got really lazy. Strat and structural discontinuities. We are resolving faults, stratal variations in the Buddha and Eagleford, and unconformities and karsts in the Austin Chalk. And so let's look at the examples. This is part of the testing that I went through 12 to 50 hertz and found subbands for the linear subbands to be giving me the response I was looking for, detail in stratigraphy, not amplitude, but in the stratigraphy. at 24 hertz for the linear, and for the octave subbands, 26.5 hertz. So I took each of these subbands and made them a base survey, reran all of the instantaneous attributes again, and got some of these results. Okay, this is my illustration of why you wouldn't want to leave your data unpicked on every line, because you're going to get a footprint. This Austin chalk that was given to me was picked on every fifth line, which is plenty to get a good result. These are, again, what we call ghosted horizons of the classification on the Austin chalk horizon. This one at the linear subband, linear trace subband, which is all I proceeded with, at 24.7 hertz and at 26.5 hertz. Pretty close. And here we see this fault with an orientation unlike any others. It's very straight and narrow, but I think it's real. There are other things that I wanted to make faults, but with this kind of quality of data, it's a little more difficult. And I believed I sort of saw it, but maybe not as well on this subband. So this is typical, variability. When you change the statistics or change any part of it, you're going to get changes. Okay, this is where it gets more interesting. I'm down to my last handful of examples here, but suffice it to say for this one, and I've got the extraction, what I call the extraction color bar on again. These are cross lines instead of in lines. We're in this vicinity and we're looking at neighboring wells, 3 and 4. And in both cases, the bottom of the Eagleford is identical. And then I turn off a couple of colors in here, and everything goes away at well 3, and hardly anything goes away in well 4. And these colors are unique to well 4's area. So you see how there's subtle variation can occur very quickly. At the Buddha, in this color bar, this purple is now the basal clay shale, and that's in both views. And this orange and red color is in both views, but it looks very different in these well locations. This looks scooped, and with the judicious turning off of these two colors, you see that they're isolated and scoopy looking, when this just looks like railroad tracks over here at this well. Don't know what it means, but you can't interpret what you can't see. So you need to see it, calibrate it, if it's important to you. This was less important to me, but learning about spectral decomp was, very important to me. I had never worked with it before. Okay, this is now a Timeslice in, by the way, that previous one was just the 24.7 hertz. And this is just the instantaneous SOM on spectral decomp 24/7 base survey. And at this depth, 2.5 seconds, we're looking at the up section is down, the down section is up, and we're seeing a couple of things. First of all, remember the purple, orange, red that we just saw in the 3 and 4 well? Well, that, one of them laps out and they interfinger, and then they end up being yellow and an orangish color, an orangish red color, something, none of the above on the other side. So in the frequency domain, something is changing there that didn't appear to vary using the SOM color bar before on the basal clay shale and the Buddha. Okay? Has some meaning. This purple for the basal clay shale becomes the lowest, most olive zone over here. The other thing is this very cool compressional fault, and you can see the little dimple there? You can see it in the nearby cross line as well. See the little dimple? And that's that same fault. Looks a lot like the one in the bacon strip that I showed you, the major fault. But also, so the Eagleford is very, its thickness doesn't vary too much. The upper Eagleford is, I love that the marl is blue colors, so it helps me think about carbonate.
Where's the ash bed on?
The ash bed is not showing up here like it did before. Again, the ash bed in frequency domain, in the frequency may not be that different.
But it would be green and...
It should be, right up there. And I'm not saying that the green couldn't be it. I just haven't typed these to see. I was too busy being fascinated by the apparent karsts and faults and other things. And
There's an unconformity at that line, at that boundary.
oh, you think? You want to see it? You straight man, you. Oh my, you mean there? Isn't this great? Here, I just turned off mainly, there are some variants in the total color combination, but by and large, this part of the upper Eagleford is nearly identical for wells 6 and 8. Not much change, they're pretty close together. But I turned them off here and didn't turn them off there so that you could see it, everything, and you could see the unconformity of the Austin chalk going into the, and this is still 24.7. But now we're down here where all of this Buddha is that yellow-orange that it got to be as you went up to the northeast. And again, these are, you know, the deviated wells and so forth associated with the vertical ones when we have that information. And then here's another one. Now we're on the 26.5. So we've switched to a different SOM, and as a consequence, the colors look a little different. The upper Eagleford is now, you know, in part of these colors, and there's a color that I turned off just to accentuate in the Eagleford itself, just to accentuate this unconformity and the big facies change that happens just inside whatever this feature is. You know, I haven't extracted these, so I don't know what they look like in 3D. I mean, this is such an embarrassment of riches. I could spend my entire life probably, you know, working on these things. But part of the reason for presenting is finding out what's been critical and important to you guys who really know the Eagleford. You know, my best hope is that you're going to say, God, I've wondered about that, and maybe that's what's happening. Okay, so that's that. And I think this last one is the one, I used to call this odd feature. It's clearly a karst, but here's the conventional inline segment. Here's the interval between the top of the Austin chalk and the Buddha. This is 110 mils, so you're seeing the whole schmear. The Buddha is in these blue bands. I've turned off some Eagleford. Where did I put them? I can't even read that myself. Okay, the Eagleford Shale numbers that are cut off, so 3 of them are here, and then the upper Eagleford, a couple of things have been turned off there, again to see the disconformity. But look at that sucker. This dark brown is both outside and inside. I presume that could only be a karst. That isn't a conventional channel or anything. It's got to be a karst of some sort. But it fascinated me. I just kept bumping into these things, and so I always capture when I bump. And so that's my last slide. I'm just going to recoup the conclusions that we can. I think you would have to agree that we can see the upper Eagleford marl distinctively. We can see distinctly. We can see the ash beds distinctly. We can see the basal clay rich. That means we can extract away the non-reservoir from the reservoir. We clearly have a calibrated hold on low resistivity, high resistivity. Mixed happens when you go laterally from high to low. It happens more often. I've never seen such porpoising as was done in some of these wells. Sometimes pretty much missing everything. But anyway, so we can find these zones, we can see these geobodies, we can resolve faults, and we can see things with the spectral decomp. What I like to tell people is if you want to prognose or calibrate your wells better, or if you want to geosteer better, which was one of the guys from the company that I worked through, when I reported this the last time, he said, because they needed help, they were geosteering on dip. Here we can, because we know exactly where these things are, now you clearly want to be in depth instead of time, but because we can work in depth, we can work on 2D volume, 2D surveys and the like, but if you want to geosteer better, we can get you there. If you know that this is what you want, this high resistivity thing like that example I showed, you won't miss it like they did, okay? And if you want to evaluate your leasehold, this was the deal with the first data set I worked for a company that bought the software. If you want to evaluate your leasehold with more confidence, you might want to think about using this tool. And thank you. That was it. I hope I didn't. Not too bad.
And as a token, of appreciation, we are giving you the whole state of Texas in the Rattlesnake Limestone, which is from a secret quarry here in the state of Texas.
Very nice.
Thank you.
Thank you. Very nice.
As you all leave, take your name tag